Here we're going to explore the concept of equilibrium. We're going to start by looking at the equilibrium of a particle. Newton's first law says that an object that is at rest will remain at rest, or an object that is moving will continue to move in a straight line with a constant speed, if and only if the net force acting on this object is zero. This is one formulation of Newton's first law. It focuses on the idea of an object at rest will remain at rest, or an object that is moving will continue to move in a straight line with a constant speed. In either of these cases, what we're seeing here is that the acceleration is zero. The object at rest remains at rest means it's not moving. Straight line, constant speed means there's no change in magnitude of the velocity, there's no change in direction of the velocity, so the acceleration must be zero. If and only if is the biconditional. It means that if one is true, the other is true, and the net force acting on the object is zero means that there may be forces acting on the object, but those forces cancel out in such a way that the net force is equal to zero. Because of this biconditional, that means that knowing one of these things implies the other one is also true. Thus, if we see an object that is in equilibrium, if we can look at an object and we can see that its acceleration is zero, then we can conclude that the vector sum of the forces acting on it is also zero. Basically, that the sum of all the forces is zero. Such a particle is said to be in equilibrium if it has zero net force acting on it. Technically, there are two types of equilibrium. There's static equilibrium, where the acceleration is zero and the velocity equals zero. That's what we're going to focus on here. Technically, dynamic equilibrium is a case where the acceleration is zero, but the velocity is not zero. That would be the object moving in a straight line at a constant speed. Technically, that's equilibrium from the mathematical perspective, but it is not as practically applicable as static equilibrium. If we observe a particle to have zero acceleration, we can conclude immediately that although there may be forces acting on the object, the net force is equal to zero. Remember that this symbol here is the null vector. The null vector is a vector that is zero in each of its directions. So it would be zero in the x direction, and zero in the y direction, and zero in the z direction if we wanted to make this fully three-dimensional. We know vector components cannot affect one another, so that components in each direction must equal zero independently and simultaneously, or the components in the x direction must all cancel each other out and become zero, and all of the force components in the y direction must also cancel out only other y components. If you have some arbitrary force, where you have a force vector that has a magnitude and a direction, what you typically want to do is express this force in terms of its x and y components, so that you can put the x components with the x components, you can put the y components with the y components. Also, what this does is fx and fy are two totally different values, but they aren't really independent of each other. They both depend on the magnitude and the direction, so it gives you two variables that are present in both of these equations, and you often end up with a system of equations to solve.